Okay, so here we go. All right, so like Dr. Kelly said, I'm going to talk to you guys about progress that I've made throughout my thesis towards uh, building a plasma-based optical computer. Here's an idea of what we're going to be talking about today. So the first 7 slides or so, I'll just give you guys some background and motivation as to what we're doing here. Talking about electromagnetic waves, how we manipulate them for communications applications, and then forward looking to optical computing. And then I'll talk about the unique dielectric response of plasma and how that allows us to manipulate electromagnetic waves in unique ways and interesting ways. And then I'll talk a little bit about some of the prior efforts in the Stanford Plasma Physics Lab when I arrived. And then just to sort of set the stage and explain our next step, which was to move up the complexity of our devices to take this sort of plasma-enabled electromagnetic wave manipulation further. So the first thing we moved to was three-dimensional devices, and I'll explain what I mean by dimensionality later. And then also a couple of magnetized devices. Okay. And then after sort of demonstrating the complex behavior that we can get with these plasma optical devices, I'll spend about the second half of the talk or so talking about inverse design, which is a methodology that allows us to really pull out all that potential complexity, and then build devices that are capable of doing things as complicated as computing applications. So we'll first talk about wave manipulation with plasma, like I said. So the main focus of my thesis and today's talk is the manipulation of electromagnetic waves with plasma elements. So plasma has this unique dielectric response that's tunable. Okay, it allows for optical devices that are switchable, reconfigurable, and capable of performing several completely different functions. So you can have one device that maybe does two completely different things. Okay, and then on the right side of the slide, you see some examples of devices that we'll talk about later in this talk. So eventually, I would like to perform computational tasks with these devices, and that's what we're working towards. So I'll start by just saying that the interaction with and manipulation of light is fundamental to modern technology. I'm sure all of you are aware. This is just your standard figure of the electromagnetic spectrum. And then the icons on the bottom sort of give you an idea of the different types of technologies that are used, in that frequency band of the spectrum. My experiments live in the microwave regime. So we're sort of like interfacing with these communication applications. But one type of technology you don't see up there is optical computing. Okay, and let me explain a little bit what optical computing is and why we're pushing towards it. So conventional computing technology is beginning to hit a physical limit. You can see the progression of Moore's law on the right side of the slide with that figure from TSMC. Our smallest commercially available transistors have a physical gate width which is on the order of 50 silicon atoms wide. So we can't really push them to be any smaller. We can't. And if we want to continue to scale our computational capacity, we're going to have to turn to computing technology that's based on different physical phenomena. So I'm sure everybody here has heard about quantum computing, but not everybody has heard about optical computing, which is where you use electromagnetic waves to perform computational tasks. So optical computing devices come in many forms, and they can often perform very complex tasks in the time it takes for a light signal to pass through the device. So I've given a couple of different examples of one-shot computing devices, is what I'll call them on this slide. So on the top right, that's what's called a diffractive deep optical neural network. And essentially what happens there is you send in a spatial distribution of light, in this case, a handwritten digit, and then that really complex, all those complex dielectric layers that are printed out or created via lithography or some methodology redirects that light to a detector that tells you, hey, this is a 5. Okay. And normally you would do that, computationally through like a convolutional neural network, a lot of matrix vector multiplication. But in this case, the light just passes through the device and the computation is being performed essentially instantaneously. Okay. And then like this device here on the bottom left, that is actually a matrix vector multiplication device. So you encode an input vector into the 3 modal inputs on the left, say for this device right here. And then the way the light propagates through the device, it performs a multiplication by a complex valued matrix that's represented by that complex sort of dielectric structure within the device. Okay, and so you have this benefit of all these computations being performed at the speed it takes for light to go through. Okay, that's instantaneous, but it also, you don't get component heating, and this is important because our computing architectures now are limited to being two-dimensional. You can't stack them up because things get hot, and you wouldn't be able to do that. So that's another advantage in optical computing devices. Now you can actually access the third dimension and make much more complicated computer architectures. Okay. And so plasma in particular may be well suited for optical computing because it allows several functions to be encoded in a single device. So the problem with these devices is that they're static, they're frozen in. So that device in the top right there is only ever going to be able to differentiate between handwritten digits. And these matrix multiplication devices, they can only represent a single matrix. But if you were to make that device out of plasma where the elements are tunable and you can change how the device is manipulating the light, you might be able to have a diffractive deep neural network that has one configuration that will differentiate between handwritten digits and another that's handwritten letters. And then, or in the case of the matrix multiplication, you might be able to represent an arbitrary matrix. Okay, so that's why we want to push forward and be able to make these sorts of devices with plasma elements. So this slide sort of represents how, at least with non-magnetized plasmas, how we can manipulate light. Okay, so by tuning the plasma frequency for like just kind of a non-magnetized isotropic plasma in thermal equilibrium, you can make the elements of our device either stretch or speed up electromagnetic waves or act like a metal. So this is the plasma permittivity. Since this plasma is isotropic, the best way to understand this permittivity is just the index of refraction squared. Okay, so omega p is the plasma frequency, and then omega is like your operating frequency, and then gamma is your loss or your collision frequency. Okay, and then the important thing to realize here is that the plasma frequency the plasma frequency squared is proportional to the electron density, and this is the parameter that we can change by changing the amount of power that we're supplying to each of our elements, basically. So you can increase the current to your discharge bulb or whatever, and you get a higher plasma density. And so what this plot is showing you here is the x-axis is the operating frequency normalized by the plasma frequency. So like right on this red dashed line, the two are equal. And when you have operating frequency that's higher than the plasma frequency, this is the underdense regime, your waves are stretched because your permittivity is between 0 and 1. Therefore, your index of refraction is also between 0 and 1. And the waves are stretched out and the phase velocity becomes like superluminar. It's higher than the speed of light, not the group velocity, of course. And then on the left-hand side, you end up with metallic behavior where your plasma density or your plasma frequency is higher than your operating frequency. And what I mean by that is because the permittivity is negative, the index of refraction now becomes imaginary. You have evanescent waves in your material. They're not allowed to propagate into your material, and it reflects off the material. We call this the overdense regime. And so if you often will try to stay sort of in this regime, like all around 1 here, all around the plasma frequency and operating frequency, and if you play in that area and tune the plasma density, you can cause the elements in your device to have a totally different interaction with the light that's propagating through the device. Okay, and we'll talk about later how the types of complex functionalities and behaviors we can get by taking advantage of this. Now, when the plasma is magnetized, we can attain permittivity values beyond the limits of the Drude model. So you saw on the previous slide, the permittivity value is limited on the upper end by 1, but when you magnetize the device and take advantage of resonances, which I'll point out on these plots on the left in a moment, you can attain permittivity values that are much greater than 1. So what these are on the left are called dispersion diagrams, and they're basically telling you the allowed modes within a plasma. In this case, when the wave is traveling along the magnetic field. In this case, when the wave is traveling perpendicular to the magnetic field. But the important thing I want to point out is that these horizontal lines that go off to infinity over here are what we call resonances. And what's happening is K, which is just 1 over the wavelength of light, basically, right, is going to infinity, which means that your wavelength is going to 0. Your waves are getting really, really compressed and moving very slow. And that's the same as having a material with a super high index of refraction, okay? And so your permittivity runs off to infinity. And if you can utilize these resonances to sort of tap into a whole, the whole range of permittivity values that you would want to get in the device. So by magnetizing plasma, you can take it even further. And we'll talk a little bit more about magnetized plasma devices later too. So when I came here to Stanford, our lab was engaged in the construction of plasma-based optical devices that utilize mostly two-dimensional photonic crystal structures. So you can see here, it's like a square array of plasma elements. And again, I'll get back to the dimensionality. I'll explain exactly what I mean by that. But it's really just the number of sort of heterogeneous directions where if you the material changes. But I'll be more clear about that in a moment. And so these were sort of crystal resonators, waveguides, bandgap devices. A bandgap device is a device that doesn't allow a certain set of frequencies or colors of light through it. That showed tunable performance. You could move the band gap in frequency space, but the really what these devices were is like they were a bunch of copies of the same element arranged in a two-dimensional configuration. Here, this is actually a bunch of plasma filaments that are created by a microlens array. So it's actually quite small. So it gives you an idea of the types of different plasma elements that you can have in your devices as well, not just these large discharges that are in the microwave regime or operate in the microwave regime. So those larger physical scales. So we'll now talk about the first step that we took to sort of see, okay, how can we push this further? And that's like moving from 2 dimensions to 3 dimensions. And so like I promised, I'll explain what we mean by this dimensionality and what a photonic crystal is, okay? So when one creates a medium that uses a periodic dielectric structure, you enforce a block periodicity for the waves traveling through it. And depending on the properties of the pattern material, certain modes are going to be allowed in the medium and certain modes are going to be disallowed. So on the top right, all the way to the right side on the top right there, you can see these photonic band gaps can occur where no mode in that frequency range from 0.15 to 0.25 roughly is allowed within the medium because of the periodicity and the properties of the material that's being stacked in this 1D photonic crystal. And again, like I said, 1D is like count the number of directions that when you point your finger, you get a heterogeneous material. So if I'm going this way, there's nothing there, and if I'm going along this way, there's no heterogeneous material. And then 2D, you can see there's 2 different directions here. But if you're going up and down, it's uniform. Okay, and so you get these photonic band gaps and these complex sort of dispersion structures. And when you move to 2 dimensions, you do get more complex dispersion, in particular because you even get different dispersion or different sort of allowed modes if the electric field is polarized across these sort of columns here or along the columns. We call this the TE polarization or the TM polarization, and that's represented by the blue and red modes in the dispersion diagram on the right. And you see these modes look really complicated, but it's like these things can tell you things about like the group velocity of your wave, and you can learn a lot about how your modes are propagating through your medium by looking at those diagrams. But for now, you just know that, okay, that's a 2-dimensional dispersion diagram. And we can look at that and come to conclusions. And we'll talk a little bit more about some 2D dispersion diagrams a bit later. But that's the idea behind photonic crystals in general, okay? So in our first 3D study, we utilized a layer of underdense plasma. So now we're in that 0 to 1 regime, okay? To tune the response of a 3D photonic crystal bandgap device. Okay, so these are 2 3D photonic crystals that are cubic lattice, dielectric photonic crystals. These are silicon nitride bearings, and they're just in a simple cubic lattice. And then we put a layer of underdense plasma, so our operating frequency is actually much greater than the plasma frequency within these bulbs, to see if we can see some tunable performance, even when we're in this really underdense regime where the plasma is almost very close to behaving like a vacuum medium, okay? And because the plasma is significantly underdense, the response is very small, but it's still measurable and repeatable. So we confirm this through simulation. You have all these different strong band gaps in this band gap device, and when you turn the plasma on and off, you see these like shifts of the band gaps, minor shifts of the band gaps left and right, and then also increases and decreases in attenuation on the order of 5 to 2 dB, which isn't huge, but the fact that it's repeatable and measurable sort of is promising because you can achieve this with a really underdense plasma. Okay, and then like a more robust iteration, of course, would allow you to have a much stronger level of reconfigurability in performance. But in practice, this is sort of nice because if we wanted to operate at really high operating frequencies, say like optical frequencies, you could still use plasmas that are significantly underdense and get this tunable performance. Okay, so that was the first main result that we got. And then we wanted to move on to a three-dimensional device that was composed entirely of plasma elements. Okay, so this is a 3D wood pile structure photonic crystal. And this is an interesting device because, like I mentioned before, if the device was all sort of rods oriented in the same direction, you would get totally different dispersion in physics, whether you were aligned along the rods or across them with your incident light, right? And your incident light polarization. And this device sort of, it forces both of those physics to be at play at the same time, okay? And so it shows an interesting coupling between those two different types of physics. So here you see coupling between these things that are called localized surface plasma modes, or LSP modes, in the horizontal rods, and Bragg interference in the vertical rods. So localized surface plasmons are essentially just these modes. It's like a resonance that occurs at certain frequencies, and you can see them zoomed in here. All these electric field vectors are like spinning like right around the interface between the plasma and the air, or the plasma and its like quartz container. And that's indicative of an LSP mode excitation. But the thing to keep in mind is essentially it's just like a loss mechanism. It's some of the energy of the incident light is coupling into this resonance, and you're sort of losing it on the other end. So you get these really deep band gaps. So this orange line is when just the horizontal rods are on. So so you're exciting these LSP modes. And then this is where that resonance is. So you can see the really deep band gap when you excite those LSP modes. And then in the other rods, you know that you can excite LSP modes. This only occurs with the TE polarization. And so you know all the interference in that case is just normal Bragg interference, just like constructive and destructive interference that comes up from like any sort of photonic crystal structure. And so the interesting thing that you see here is that particularly at this frequency that's close to localized surface plasmon resonance frequency, when you put all the rods on, you actually get an attenuation that's higher, or a deeper band gap, than if you were to add the two cases with just the horizontal bulbs and the vertical bulbs on in series. So like if each of those is performing like a filter and you put them in series, you would actually get a smaller attenuation than if the rods are all interleaved with each other. And that shows you that you're getting this sort of interesting coupling between those modes in the vertical and horizontal rods. So you have all that complex behavior going on with this 3D device that's composed of just non-magnetized plasma. It's nothing super crazy. Okay, so then that we've demonstrated this complex behavior with 3D devices. We've taken that step up, but what about magnetized plasma? Okay, and so that now we step back down to a two-dimensional device, and we'll demonstrate some really strange behavior, like cloaking, for example. Okay, so some dispersion topologies, which is just a word for the shape of the dispersion bands in the diagram that I showed you, result in really strange behavior. So this is what's called Dirac-like dispersion. So in a 2D photonic crystal, the dispersion bands are actually these 2D surfaces, okay? And Dirac-like dispersion is when you have a linear conical intersection that has a flat band going through the intersection. So it's a threefold degeneracy in the dispersion bands. And the reason why we call it Dirac-like dispersion is because it resembles Dirac cones that you find in graphene at the Brillouin zone boundary for my solid state folks out there. But the important thing for photonics is that it's actually just this accidental degeneracy that happens. We can't really predict the exact parameters that are going to lead to this phenomenon. But what you have here is you have this linear branch that has negative group velocity, and then it transitions at a single point to a branch that has positive group velocity. And what that means is that the group velocity has to pass through zero. And because you have this degeneracy between the three modes, you're allowed to couple into a zero index medium. And what does a zero index medium mean? Okay, so a zero index medium means that your wavelength is going to infinity, and your phase velocity is going to infinity in the object. So if you impinge an electromagnetic wave source on the left at the correct frequency, this is a photonic crystal medium, the entire medium is one phase at once. And then the light just travels outwards out of every sort of open path of the device. And then if you embed an object in the photonic crystal, because the wavelength is infinite, the object looks infinitely small to the wave. So the wave just goes right around it and ignores it. And it propagates around the object as if it wasn't there at all. So this is really weird behavior. And we were like, okay, how can we try and, this is just with dielectric material, but like, how could we do this with plasma? Okay. So if we want to realize this direct light dispersion in a plasma photonic crystal or PPC, we need to utilize the cyclotron resonance, okay, in the lower RCP mode of the magnetized plasma dispersion, because we need epsilon greater than 1. Remember, on non-magnetized plasma, the epsilon does not go above 1, okay, and we need that to realize this Dirac like dispersion. And so we tune the magnetic field just so that we can reach the desired permittivity value at the desired frequency. And this is sort of the configuration that you end up with. So there's like square lattice of plasma rods coming out of the page, and then the wave is traveling along these rods. But there's a hiccup in all this, okay? This branch is right circularly polarized light, okay, which is a composition of the TE and the TM modes at once. And both of those react differently in this 2D configuration. So if you want this to work, you need to find Dirac points that are coincident in the parameter space of frequency and dielectric constant and rod spacing for both the TE and TM polarization. And then, like I said, these are accidental degeneracies. So there's no way to predict or really analytically find these coincident Dirac points. What you have to do is a parameter sweep. And somewhat miraculously, you can actually find such a pair of Dirac points. So this is the trajectory of a bunch of different Dirac points through the relevant parameter space here. And you can see that this red line and the blue line that represent a TM and a TE Dirac point respectively of higher order than lowest order are actually almost completely overlapping for a fairly large region or area in the parameter space, which is kind of remarkable. But you can see the bottom right, those are the two Dirac points that are on top of each other at the same frequency. And so we come up with a configuration of plasma density and magnetic field that allows us to hit these coincident Dirac points. And then sure enough, and again, these are higher order Dirac points. So the fields are not going to be as clean as the figure I showed you before. But even still, the plasma photonic crystal at this magnetized plasma photonic crystal for both polarizations almost completely removes the wake behind the object, at least in intensity. And so you can have this device that's going to have this very strange behavior. In fact, like because you have this behavior, you could have like 90-degree bends or sort of a strange path, and you wouldn't incur a lot of losses. Your intensity front would be almost uniform on the other side. So that's one of the very weird things that you could achieve if you magnetize your elements, okay? And then another strange, what we call topological phenomenon that can be observed in magnetized photonic crystals, plasma photonic crystals, is the unidirectional edge state. So in our lab, we showed via electric field measurements that our cylindrical gaseous plasmatic sources have a pronounced gyrotropic response, which biases the scattered field in one direction. So what that means is that you have an incident light on our discharges, which is magnetized, and you can see the scattered field is sort of biased in this case about 30 degrees to the left or right, depending on whether it's biased into the page or out of the page. Okay, and what you can do is you can set up the situation where you're in the band gap of the photonic crystal. Okay, so that means that the light is not allowed to propagate into the photonic crystal. You get Bragg interference, okay? And then if you put another mirror on the left side here and you try to excite, you try to like pump out some electromagnetic energy here, it doesn't have anywhere to go. It can't go into the crystal because it's in the band gap. It can't go this way because there's a mirror here. But because you have this preferred scattering direction, what happens is that the wave starts to make its way along this border. And you can sort of make this gap as small as you want, and that mode will start to travel in one direction. And no matter what you put in its way, you could put a sharp defect, or you can make it go around a weird path. It would not backscatter at all. It's called backscattering immune. And so, you can imagine there might be some interesting communications applications for a device like this, but it's very strange because it's it will never travel backwards. It only goes in one direction. So we were talking about this, and we thought, okay, let's see if we can demonstrate this with our plasma sources. So the experimental setup is like this. It utilizes a 3D printed scaffold with 3D printed walls that we electroplated with copper to serve as that PEC mirror, or that boundary. Okay, and you can see the rods are oriented within a Helmholtz coil that gives you that quasi-uniform magnetic field. And then you try to excite the edge state by putting the source in the left here, and then you have this probe on the side that tries to measure the edge state as it moves around the edge of the crystal. And so when you use the experimental parameters that we have, you get with a conservative collision frequency, you observe the presence of the one-way edge state. So when the magnetic field is zero, there's no band gap there. So the fields are sort of allowed to penetrate the photonic crystal. But when the magnetic field is switched on, you're in the band gap of the crystal. So the fields are not allowed to go within the crystal. But because you have this one-way edge state that exists, it'll go in this direction and sort of happily go around the crystal. And then you can see that when the bias switch direction, you get the propagation in the other direction. And there's no edge state that goes this way because it's disallowed because of that bias scattering direction. Okay. So then when I perform the measurement, we observe about 10 dB isolation in the collect frequency band. So this right here is the dispersion diagram for the magnetized photonic crystal. It's very complicated, but the point to realize here is that this is that band gap that we're using. And then it's at the same frequency band, we see this sort of like one-way bias propagation of light with just this field probe, which frankly does not couple with this frequency very well. That's why we're designing a new experiment that will hopefully couple into these edge states a little bit better. But still, this is sort of the first demonstration of a one-way edge state in a device of this nature with a gaseous plasma element. So that's exciting. So the idea here that I wanted to get across just by showing these magnetized devices is that when you magnetize plasma, you can get super strange things to happen. So we saw when you go to 3D, you can get these cool behaviors, these tunable devices. But when you magnetize devices, things get very strange. Okay. So then we now turn to inverse design. Okay. And this is what we'll talk about for really the rest of today. So to create the following devices, all the devices we talk about from here on out, we use a technique that's called inverse design. Okay. And it's basically what it sounds like. You come up with a priori performance metric, and you find a way to map like parameters that encode a domain to that metric in a way that's differentiable. And then that allows you to sort of like iteratively improve your device. Okay. And so these devices end up looking like this. They're almost like random to the eye. But what they can do is something interesting. Like for in this case, you have this complex structure here, and you have an antenna radiating electromagnetic waves into the material, and the different frequencies are directed in different directions. Okay, these are the types of weird things you can do with an inverse design device. And as you can see, like this is the type of complex behavior that we need for like an optical computing device, for example, these really strange demultiplexing effects where you're sending the different frequencies in different directions. So the most sophisticated inverse design devices today can achieve grayscale values for the dielectric constant. What I mean by that is you have these two extremes, epsilon1 and epsilon2, and by layering in your manufacturing process, you can get values in between those values. But again, they're still static and single function. Okay, so you can't by static I mean you can't turn them on and off. You can't tune them. You can't tune them for the actual function that they're meant to do, and then you can't do more than one function with the same device. So with a plasma, you could, since the plasma density is variable, you can perform many different functions with the same device. And that's why we want to make this sort of device with a plasma element. And so what we do is that we optimize what I'll call plasma metamaterial, or PMM, from this point on, with the plasma frequency of the elements in the device as the parameters. So this is like your parameter vector, and then you basically each of the elements in this vector corresponds to like one of the elements in the device, and then you use that to create a relative permittivity domain that you then feed to a frequency domain solver in our case, and then you get your electromagnetic fields out, and then you use those electromagnetic fields to evaluate your device by saying you want a high intensity at a certain frequency at this exit of the device, but low intensity in a different area, for example. And then you compute a gradient with respect to your input parameters somehow. In this case, we use forward mode differentiation, or ceviche, software that's written by our collaborators over in electrical engineering. And the way that works is basically the solver itself is actually computing the gradient or the Jacobian as it computes the fields. So then you can access that gradient at the end of the calculation. And we use that to iteratively improve the device and adjust the parameters every iteration. So you actually have to run the simulation every single time. And this requires you to use like a simplified model, in our case, a two-dimensional model. And so we can't, with the computational inverse design, we can't actually use a 3D device or a magnetized device, even though those devices would give us a higher degree of complexity. But we'll talk a little bit how we'll address that problem later. So device is really simple. We thought, okay, we're just exploring this. Let's just do a 10 by 10 array of plasma discharges with input and multiple outputs. The inputs, these waveguides are not designed to couple with the medium very well. They're just dumb square waveguides. We wanted to see what this could do. And then also for this first exploration, these plasma elements are super simple. It's just a uniform cylinder of plasma, okay? Just wanted to explore what was possible. So the sort of simplest objective for this device is just a low loss mode preserving waveguide. And so what you're looking at here on these figures on the left, these are your field intensity or field magnitude with the source on the left. And then this is the relative permittivity domain. You can see all the different rods. Basically, the darker red the rod is, the higher the plasma density or the higher the plasma frequency, okay? And the main thing that I want to point out first when I first showing these results is that, if I showed you this, you would not be able to tell me what it did. Because that's one of these hallmarks of inverse design, is that it gives you this non-intuitive designs that seem very strange and something that you would never be able to produce using like a human design. And it sort of suggests that we're able to achieve or get at these much more effective designs through this inverse design methodology. Okay. So in each of these cases that you're seeing here, the operating frequency is actually, very reasonable, allows the plasma frequency to be very reasonable in the order of 6.5 gigahertz. That's not hard at all for us to hit with our sources. Okay. And then we stepped up the objective a little bit in complexity, which is what you're seeing here is called a demultiplexer. And what it does is it directs different frequencies to different exits. So when you send in, this is a non-dimensionalized frequency, so don't worry too much about what that is. But when you send in omega equal 1, it goes to the top exit. You send in omega equal 1.1, it goes to the bottom exit. Okay. And the reason why I have a frequency label on these plots is because for different operating frequencies, your plasma has a different permittivity. So you have to make sure you take that into account. So in general, the reason why we chose demultiplexing is because it's actually a really important function for achieving a high degree of parallelization or parallelism in optical computing devices. That's one of the advantages of optical computing devices, that you can encode different information in different frequency bands and then send the same light at the same time through your device. And if your device sort of is able to split those frequencies apart or do different operations on the different frequency bands, then you can achieve that parallelism without any sort of cost to your device, any heat or anything like that. And so with the exception of the low frequency TE designs where you're coupling into those localized surface plasma modes that I mentioned before, you're getting that loss by coupling into those modes. We see consistently good performance. So the next step is, okay, that was like promising results. Okay, with that really simple model, we were able to get those. Now, what if we want to realize this experimentally, we're going to have to use a much more realistic model of the plasma elements than just a uniform plasma rod, right? So we refined the model. So we added a non-uniform density profile within the bulb. We added the envelope, the quartz envelopes of the bulb, and we also introduced some loss or collision frequency of the electrons with the neutrals. Okay, and then looked at this, basically the exact same devices. And we also looked at the random perturbations of the device, and I'll talk about that in a couple of slides. So with those non-ideal factors considered, the waveguide and the demultiplexer still function very well. So the only thing is that these devices are much more difficult to optimize now. You have to do it in multiple steps. And if you guys are curious, I can talk about that a bit more in a bit. But there's nothing disqualifying here. You just get a little bit more loss. And the devices are still performing. And so we also wanted to make sure that they were robust, because in practice, you know, we have all these sources in our lab. They're not all exactly identical. And so you can run into some cases where one or two of the elements in the device might not be exactly what you want them to be when you're trying to build the device. So we added Gaussian random noise to each element of the following form on the top right. And basically what that form allows you to say is that if P is equal to 0.45, for example, you know, you can expect some of the rods to be perturbed on the order of 45% of the optimal plasma density. And in what we showed, in fact, was that you had to increase P to 0.45 for the straight waveguide to actually see any serious degradation of performance. And then likewise with the bent waveguide, you have to increase P to 0.39. So you would say that this is, you know, highly resistant to random perturbations. We shouldn't be seeing plasma density values that are off by 40%. And then demultiplexer is likewise very resistant to perturbations, despite its more complex objective where P had to be increased all the way to 0.34. Okay, so these results are encouraging. We're like, okay, we actually can go ahead and spend the energy building these things. It looks like they're going to work. But first, to really explore this device's potential, we remove all the non-idealities, and we can achieve a fully functional logic gate. So this is Boolean logic and and/or logic gate, and this is a non-linear objective that's being achieved by devices with just inherently linear physics, and there's a lot of loss that's allowing it to do so. But really what this shows is that, you know, you even with this really simple device, just a 10 by 10 array of non-magnetized elements, if you use this inverse design methodology, you can achieve this really complex, you know, optical computing style functionality. And so, you know, it holds a lot of promise going forward. So, but like I said, we wanted to build these. Okay, so the first order of business, if you want to build this device, is you have to map the power supply settings for each of the bulbs to the average plasma density in the bulbs. And it's difficult in practice for a number of reasons. Like we don't know the fill pressure of the bulbs exactly. We don't know the gas temperature of the bulbs exactly. The bulbs are AC discharges at about, like, you know, on the order of 30 kilohertz or so. And so you also, they're at a density range where you can't use diagnostic, like an optical diagnostic, for example. We can't stick a probe in them because they're sealed, and we'd have to, you know, there's no way to make your way in there. So the way we have to do it is by measuring the voltage and the current going through the bulb, and then using a kinetic model, like a well-validated kinetic model of a DC glow discharge. Okay, and there's a bunch of factors you have to take into account there, like the cathode fall voltage and all this physics relevant to glow discharges. But the bottom line is that we sweep a bunch of different cases. Okay, the range of fill pressures that we believe exists, as well as the temperatures, and then we sort of put all those different cases on one plot, and you see that you're sort of, this is your range for your power supply. This actually should be current here, not voltage. But there's two different ways that you can operate these when you use a DC power supply. You can operate in a current limited mode or in a voltage limited mode. The voltage limited mode allows you to access plasma densities about, you know, 3.5 to 13 gigahertz. And then if you want those lower plasma frequencies, you operate in the current limited mode. But basically, you put all of these different cases on the same plot, and then you come up with this just sort of like quasi-experimental fit that maps your power supply settings to the average density in the plasma elements, or the average plasma frequency. And so with these functions here, the red one and the brown one, we're able to take a plasma frequency from, which are the optimal, remember, the optimal parameters from the simulation and from our optimization scheme before, and we can map those to a voltage and in a current setting on our bulbs. Okay. So this is sort of a cartoon of how the system works. It's just it's each discharge itself controlled by a DC power supply that's connected, and in between the DC power supply and the bulb is a DC ballast. So what this does is takes the DC output of the power supply and converts it to an AC signal for those AC plasma discharges. And then the power supplies are on RS-45 serial communication buses. Okay, and there's about 25 power supplies to each bus. And right now we have 4 buses, so we can do up to 200 bulbs at once. And then, through a USB RS-45 converter, I wrote this in situ library that allows you to take those optimal parameters that we got from Ceviche, from the inverse design, the computational inverse design, and then output a distribution of plasma densities in the actual devices. This is what it looks like. So you see this very, very big rack of power supplies on the left here, and each of those are connected to these DC ballasts, which is then each of them go to the corresponding plasma bulb on the right, and then these are just your horns. And so that's what the device looks like. It's sort of in this makeshift anechoic chamber. You need to sort of protect yourself from these bulbs because they put off a lot of UV light. You can burn your skin, and they also create a lot of ozone. So you don't really want to be in the same room as them. So you close them off. So you may have noticed that this is not exactly the same configuration as in the computational study. I actually went to a triangular lattice hexagonal setup, and there's a couple of reasons for this. One of which is that when you have this triangular lattice in photonic crystal structures, it behaves a little bit better, like an effective medium. But that's not super important. But this is the schematic. Those are the sort of relevant spacings and whatnot. And then that's a simulation domain on the right-hand side. And so I wanted to really quickly sort of reiterate that those results that you saw in the computational inverse design portion was that they were very unintuitive. And if you actually try and pick the plasma densities of each of the rods, so these ones are like man-made, so to speak, you don't get the behavior that you expected. So like if you were going to do a waveguide, you would just turn the plasma elements in front of the port you don't want it to go into, the highest density possible. So it's like metallic. And then you would create this path, this zero index path, or sorry, vacuum index path through space there. And it turns out that like you would expect this to perform better for lower frequencies, because from the lower frequencies perspective, the plasma is more metallic. It reflects more. But actually at a lower frequency, it's like leaking into the incorrect waveguide even more. And so, and then this is like, I did my best at trying to design a multiplexer by choosing the plasma frequency such that at one frequency it would form like a low index bridge, and the other frequency it would be more like a barrier. And sure enough, it did the exact opposite. At 4 gigahertz, it went out the top exit, which is what I was trying to prevent. So you can't really you can't just come up with the design and get the performance that you want. You have to use this inverse design. And I just wanted to sort of hammer that home with this configuration. But these are the results that we have so far. So you have the simulation on the left and the experiment on the right. There's a couple of things. I mean, the first thing is it's very promising because you have the transmission. This is transmission basically, S21 and S31. S21 is the transmission to this port, and S31 is the transmission to this port. So you want, for this case, you want S21 to be as high as possible and S31 to be as low as possible. And we do get almost 20 dB isolation in the waveguide case at the correct frequency, and the transmission is highest at the design frequency. But there's a couple of, and then likewise for the demultiplexer, you see sort of maximal transmission in the right frequency range, and then you're still getting on the order of 15 dB isolation. In fact, even S21 has this like negative there's almost like a band gap here. But there's a couple things to point out here. So these devices are optimized at a single frequency because the frequency domain device, it's also a two-dimensional model. The plasma elements are as complicated as we can come up with, but they're, you know, ultimately this is not a good perfect model for this device. This device, as you saw, is a three-dimensional device that's in an anechoic chamber. The plasma elements, they're probably not all the same. They have a bunch of complex physics going on in the actual elements themselves. And so you get this, you know, strange behavior. Like, I don't know where this is coming from, but this would be really useful. This is a super deep band gap. And so, like, you know, that's really good isolation. And if you could predict that, then you'd be in really good shape. But unfortunately, this computational method of optimizing the parameters in silico and then trying to translate them to the real device, you're going to run into problems. So the beautiful thing about using plasma elements is that we can do this entire process, this inverse design process in situ. Okay, so you can forget the simulations. You don't, you know, whatever. You just perturb the plasma element densities, and then take the transition spectrum out, and then come up with some sort of performance metric. You want really big isolation at one frequency and another, and you can just let it iteratively train itself how to do these functions, and you just come up with a function you want to do. And the other thing is, and that's why I showed you guys those magnetized devices, is you can magnetize it. You can use a three-dimensional device because in silico, when you're doing this in your computer, we can't use a 3D device or magnetize the device because it's too complex, it's too costly. We can't run many iterations of those simulations. They take too long. We can't do like 1,000 iterations to optimize those devices. So being able to do this completely in situ, because we have these plasma elements, and no other type of materials like this where you can easily reconfigure it and change its dielectric properties so quickly. Because we have these properties, we can do this optimization fully, this inverse design process fully in situ, which will help us both when the numerical model is crude in these two-dimensional configuration devices, but it also allows us to go forth and use those magnetized elements and those 3D architectures, and hopefully eventually arrive at this plasma-based optical computer that performs really complex computing tasks. But yeah, so that sort of brings me to where I am right now. Basically, the next month or so, I'm just going to try to refine these results, and then I'm going to try and carry out that fully in situ inverse design, and maybe demonstrate one device that's like three-dimensional or has magnetized elements, and then hopefully that'll be enough, and defend a thesis and get out of here. So thank you guys for listening. If you have any questions, I'd be happy to take them now. Yeah.
Yeah, I'm wondering on that computational inverse design, it's just under constraint problem, right? Which design you choose? Like, I'm wondering, does it give you a lot of possible designs?
Yeah, and I think not only do you get a lot of possible designs, but it's like you can also fall into local minima. Like I don't think, I mean, it's not a sort of a, yeah, it's under constraint in that it's not a convex problem. So in most cases, it was sort of initialization agnostic. Especially in the idealized case, you could try to give it a random distribution to start the optimization, but you still would end up with roughly the same design, maybe a slight perturbation of the one before. But in particular, when you have the more realistic elements, there's a lot more local minima, and you can get stuck in some really poor designs. So the optimization procedure becomes a little bit more involved. So yeah, definitely under constrained, and hopefully when I try to do this in situ, I'll still be able to arrive at some really effective designs.
So I'd be curious, like, when that happens, do you ever find that you can achieve the same parameters with like a simpler design to implement?
You like same like performance, you mean?
Yeah.
With a simpler design? Yeah, I mean, I think in most cases, like when I've done like so many different, trying to achieve sort of the same thing, especially when I introduced the non-ideal factors, you know, you would end up with two totally devices that looked almost completely different, and they had the same performance. But in practice, just because this is like a 10 by 10 array, there was never anything that like was like, oh wow, that one only turns on 3 elements. That's strange. There was nothing really like that. It usually was like that sort of seemingly random distribution of plasma densities, all sort of giving you the same level of performance. Yeah. Yeah. So this slide, the right side is actually experiment. So the vertical dashed line is the operating frequency that we want to see this isolation between the port 2 and port 3. So this is the transmission of port 2, the blue line, and then the orange line is the transition of port 3. And so you want to see the blue line as high above the orange line as possible at the design frequency, because that's basically what we were optimizing for. But like you can see, there's other things going on at different frequencies that, you know, there's no way to predict because you're just optimizing for that one design frequency. Yeah.
For the experimental lattice that you're showing,
Mhm.
do you see really feasible to bring that down to a scale that is with the conventional computing?
Yeah. So there's a couple of ways to think about this. So I often get this question like, okay, how is this actually going to be incorporated, this sort of idea into a real computing device? So the first thing that I usually say is that I think a device that incorporates like plasma elements, for example, in an optical computing device, it's going to be one of those one-shot computing devices, meaning it's going to be very application specific. Like I could imagine you have a computing architecture that's enclosed in like a building or something, right? And whenever it wants to do a matrix vector multiplication really fast, it sort of sends that data to the plasma based component, and it computes that extremely fast, way faster than a normal CPU would. And then, you know, this is just kind of like a cloud computing center, and then it sends that back, and you have like a supercomputing architecture. In practice, you can shrink it down. Like you could do, there's a couple of ways that you can get those high density plasmas that you would need. I mean, for example, like metals are plasmas. They basically are. They're a sea of electrons around a bunch of metallic nuclei. And so, you know, you can actually change the plasma density of the metal through charge deposition. And that's like, those are much more difficult experiments to do. But you could shrink this down in practice to a really small device that operates at really high frequencies by using solid state plasmas or like a metal. But those experiments are really hard to actually realize. But you know, because Maxwell's equations are scalable, we can do the experiments here in this microwave regime with these less dense plasmas and learn things that we can then apply in the future to those more difficult experiments. So we want to shrink this down to those tiny scale, nanometer scales, for example. Yep.
When actually doing the experimental like in situ optimization, what's the time scale of like a given?
Yeah. So for this device here, to set all the elements, turn them on, you know, wait for them to sort of become like these sort of quasi steady state sources, and then get your transition measurement, you're probably talking about like 11 seconds. So like the contrast that with the computational one, where a single epoch or a single iteration, you know, if you're operating at a high enough frequency, is like 1,000 seconds, can take a long time. So we're running these for a long time, and so that allows you to actually do the optimization a lot faster, even for a two-dimensional device. I mean, the cost becomes completely prohibitive for a three-dimensional device, or a device that includes like an anisotropic tensor, like meaning the magnetized plasmas. So you know, being able to do it in situ is pretty beneficial, pretty fast, even if 11 seconds seems slow. It's mostly a limitation of my system that I've set up here with the serial communication and stuff. I'm sure I could maybe optimize it down a little bit, and maybe I will with the time I have. Anything else? Yeah.
In order to replicate the performance of like those one-shot devices you're getting, like tell like different numbers apart.
Yeah.
How many plasma sources? Like,
that's a great question. I'm not sure. I you know, that's why we sort of like removed all the limits for this device to see, okay, well, what can we do with just 100 elements? But in practice, yeah, like the more elements that you add, the more information you can cram in the device. And then if you magnetize the device, it's like you can cram even more information into it because there's all these sort of complex propagation structures that you can get. So it's like, I'm sure that the answer to your question is different, whether you have a 3D device, 2D device, or magnetized plasma elements. Maybe if you magnetize them in a 3D configuration, you can get it to be like comparatively few plasma elements to achieve this really complex behavior. But I think in practice, yeah, you're going to have to need like a lot of plasma elements, especially because like, you saw that the dielectric structure of that device that I showed is super complex. Like I'll just show it one real quick. Like it's, I mean, this is crazy. so if you want to be able to do that with plasmas, you're going to be able to. What with the wood pile? Yeah. So yeah, imagine you had a wood pile structure with like, you know, a certain, you know, integer multiple of that many plasma elements that's magnetized. I'm sure you could do something as complicated as those 5 layers of diffracting material.
What do you mean by that multiple number?
I'm not sure if a 5 by 5, like I don't know. My intuition says that that's not enough, but maybe if you magnetize it, I'm not sure. I've never tested it, so I can't say for sure. But I think that you can definitely the sort of information content of a magnetized plasma is so high. I just feel like you shouldn't need that many to be able to do this these complex operations. Yeah.
I'm gonna follow up just for this. So this here, like the phase map, that's basically a linear process. But you know, another way to do that is with the neural network, and the key component there is that there's a nonlinearity.
Yeah.
So is there a way that you can sort of encode the same types of nonlinearities?
Yeah. Exactly. I didn't mention that at all in this talk because I haven't done any work during my thesis on nonlinear plasma elements, but plasma is a nonlinear medium. If you use a high enough power source, the waves propagating through the plasma can cause more ionization. So your plasma density will change as a result of the incident wave, and then you get this nonlinear effect. So you can, and that's something that we've talked with the group that we've collaborated with for who wrote the simulation package, is about trying to create a recurrent neural network with plasma elements that applies that nonlinearity as a function of time with this time domain electromagnetic signal. So yeah, that definitely the nonlinearity is possible with plasma elements.
Can you go back to the results slide and the comparison?
Yep.
Surprised, I know it's a little bit of an effort. Surprised you didn't run the simulation, the optimization in this design at 4.25 gigahertz.
It actually, I did, and it was difficult because the isolation wasn't quite as good. What happens is, and I think it's because I need to fix the device a little bit, like in terms of it'd be a little too complicated to get into right here. But basically, there were too many elements turning on, and with these horns and the sort of plasma sources that we have there. Remember, we have those metallic wires. It becomes difficult at lower frequencies to get the light to actually propagate through the device and couple into the exit.
That result tells you that if you were to do the train,
yes,
for 4.25,
yeah,
you should get remarkable.
Yeah, I bet you'd be able to get 90. I bet you'd be able to get 70, 60. Yeah,
Isolation.
I 100% agree. That should be. I'll just start with these parameters and then optimize from there. So.
It's like asking a question. If I have a 4.25 gigahertz source, what plasma densities arrangements of plasma density would I think I should have to get a 70 dB isolation? That would be impossible to answer.
Yeah, there's no way you could answer that question without the optimization scheme. Okay. Well,
I'd like to thank Jesse one more time.
Thank you, guys.
And same back.